In this video, I'd like to talk about the graphs of exponential growth. And in these example problems, we're essentially going to see two different scenarios. One in which the exponential function is graphed and given to us, and we need to determine the equation. The other example is essentially the opposite, where we'll be given the equation and need to determine what the graph looks like. Now, with this one, since we are given what the graph is and need to determine the equation, there are two different approaches we can take. The first is that we can look at points on the graph and compare that to the general formula for an exponential growth equation. Or we could start with the equations and just plug in different x values and see if those y values actually appear on the graph. So let's start with the first method, since that will give us a deeper understanding of what's happening here. And what we need to do is look at the general pattern for these exponential growth functions or equations. So a general equation is going to look like y is equal to a multiplied by b to the x power. And in these equations, a, that is our starting value essentially, or it's the value when x is equal to 0. Since notice that if you plug in 0 here, you get y is a multiplied by b to the 0, and it doesn't matter what b is. Anything to the 0 power is just 1. So this would be a here. So when I say starting value, that's just the value when the x value is 0, or it's the y value when the x value is 0. And then b, that is our growth rate. So b in these equations, b is also known as the base, but you can think of it as how quickly the exponential function is growing. So it's the growth rate, or in some cases, it is the decay rate. So it depends what b is, but it could be either growing or it could also be decreasing like that. And in that case, b will be a fraction or the exponent will be negative. But we'll come to that in a later video. But usually we call this the base of the exponential function. Whatever the number is that's raised to your variable, that's the base in these functions. So we want to look at different points on this graph and try to figure out what the starting value is and what the base is, what that, in this case, the growth rate is, since this is getting bigger as x gets bigger and bigger. So looking at our graph, we can find an x value of 0 to figure out that a value. So here is an x value of 0, and notice that it goes through the y value of 5. So this equation here goes through the point 0, 5. And let's find one other point. Really, we can find multiple points, but let's look at when x is equal to 1. Notice that it has a y value of 10. So 1, 10. And essentially what we're looking at is what did we multiply by to go from our starting y value to our first y value, or when x is 0 to when x is 1. When we increase the x value by 1, what did we multiply by for our y values? And that pattern will continue since if we go backwards, since we can't go forward, since 2 is off the graph. But if we look at -1, we can see that goes through at 2.5. So -1 and 2.5, and we could keep going if we wanted. At -2, it's going to go through this point, but it's getting a little bit more difficult to determine what that is exactly. Now, once we notice the pattern, we'll know that this is at -2 and 1.25. But we'll just use essentially these 2 points here. And we just want to notice that as the x values increase by 1, the y values multiplied by 2. So they doubled. And that factor that we're going to multiply by, that's our growth rate. That is the base of the exponential expression. And we know our a value is going to be 5, since when we plug in 0 to our equation, we get 5. And whenever we plug in 0, that is what the starting value is here. That's that a value. So from the 2 points we determined, we found that a is 5 and b is 2. So our equation, y is 5 times 2 to the x. We can now test this just to make sure it's working, since we can also see it goes through at -1 and 2.5. And you can, again, just looking at the numbers, see if you take 2.5 and double it, you do get 5. So let's make a little bit of room so that we can check this. Let me scroll up just a bit. So now we're just checking that our equation makes sense. And let's plug in some different x values. Let's plug in at -1. And what we see is we get y is 5 times by 2 to the -1. Now 2 to the -1, that just means divide by 2 one time. So that's 5, well, divided by 2 or times by 1/2. But regardless, you get 2.5 there, which we do see that on the graph. So that made sense. Now, if you want to feel very confident, you can check another point. Like I said, we could check this point right here when x is -2. See that we get y is 5 times 2 to the -2. So this means divide by 2 twice or divide by 4. So you get 5 divided by 4, which is 1.25, which is what I mentioned we would expect to get here. So at -2, it does go through at 1.25. Though you can also check these primary values we looked at. When you plug in 0, you do get back 5. And when you plug in 1, we get 5 times 2 to the first, or 5 times 2, which is also 10. So it works for these 2 main points that we found originally, but it also works for these more difficult points to see when you have negative x values. And I also mentioned that you could approach this the opposite way. We could start with the equations and just plug in different x values to see if they work. For instance, when you plug in 0, you would get 5 here, which is correct. You would get 5 here, which is correct. But here, 10 to the 0, that's just 1. So you can eliminate C right away. Now, when you plug in 1, now this equation will work. We know we would get a y value of 10. But this equation would be 5 times 5 to the first, or just 5 times 5, which is 25. And we know it goes through a y value of 10, so you can see A wouldn't work. So there are 2 approaches to this, but the first approach, comparing it to this general equation here, that approach will give you a deeper understanding into these exponential growth functions.